This program is a presentation of UCTV for educational and non-commercial use only.
Good afternoon to all of you. Thank you for being here today. It is my great pleasure to welcome you to the Chancellor's Colloquium Distinguished Speaker Series for 2011-2012. As you know, this series has been to bring here, to allow us to invite and bring here wonderful thinkers and leaders who can speak to us about various issues in higher education, from teaching to research to scholarship to any other issues that are important to us, of course, as a university. And we have been very successful in the past, of course, in bringing wonderful individuals who have shared with us their thoughts. And today we have been very lucky to have with us our speaker, Dr. Ralph Cicerone, who is president of the National Academy of Sciences and chairman of the National Research Council. Ralph's research is in atmospheric chemistry, climate change, and energy, and has helped shape science and environmental policy at the highest levels, both nationally and internationally. Ralph has received a number of honorary degrees and many awards on his scientific work. Specifically, the Franklin Institute recognized his fundamental contributions to the understanding of greenhouse gases and ozone depletion by selecting him as the 1999 laureate for the Bauer Award and Prize for Achievement in Science. This is one of the most prestigious American awards in science, and the Bauer Award also recognized his public policy leadership in protecting the global environment. In 2001, he led the National Academy of Sciences study of the current state of climate change and its impact on the environment and human health. And that study was requested by President Bush. In 2004, the World Cultural Council honored him with the Albert Einstein World Award in Science. In addition to the National Academy of Sciences, Dr. Cicerone is a member of the American Academy of Arts and Sciences, the American Philosophical Society, and has served as president of the American Geophysical Union, the world's largest society on Earth, of Earth scientists. He's also a member of the UC family. Many of you may remember that he has served as the Chancellor of UC Irvine from 1998 to 2005, a period that marked the institution, the campus, by a rapid rise in the academic capabilities of the campus and, of course, its size. With us today, we also have Dean Koh. Winston Koh is a professor of physics and has been our dean of the Division of Mathematical and Physical Sciences since 2003. He will help us with moderating the Q&A session and the discussion that is going to follow Dr. Cicerone's presentation. Many of you know Winston. He has been a wonderful colleague, and he has been with us on our campus since he joined the physics department as a faculty in 1972. His research has been in experimental particle physics. He surveyed inclusive reactions as a tool early in his postdoctoral career during the pioneer days of Fermilab, and that earned him the faculty appointment at UC Davis, and of course a tenure of many, many years here on our campus. So I would like to thank both of them, our speaker for being here with us, and Winston for agreeing to moderate the session. And I will come down and enjoy with you the presentation. Thank you.
Thank you, Chancellor Katehi, for the kind introduction and also for the invitation to be here today. Some of you know that I've spent a lot of time on the Davis campus over the years, and those times have turned out to be some of my most exciting research, which I enjoyed myself. But I must say, and Larry Vanderhoff is here, I've never been in the Mondavi Center before, so this is also a treat. Thank you for helping to create it. The title of my talk today is, something's missing, Climate Change. Yeah. There's a line missing. It says, Climate Change, Human Causes and Responses. I don't know what happened. I think trying to match what the Chancellor's Colloquium series is focusing on in general, that is, issues of the day, and also issues that will remain with us for a long time and will present challenges and perhaps opportunities for humans, their institutions, their businesses, and certainly their governments. This is certainly one of the issues. I am primarily a scientist, so I want to spend a fair amount of time today talking about the science behind climate change, but also address the issues of human responses as well as human causes of climate change. I'm going to go very quickly because I misjudged the talk today for the time required, so I'm going to go quickly. I'm going to skip a couple of slides. I've asked Dean Coe to give me a few minutes of our reception time afterwards to use for the talk, so bear with me. In outline, this is what I'd like to talk about. First of all, a framework, how we go about trying to understand a system, if you will, that has so many variables as climate. Temperatures, winds, ocean currents, river flows, soil moisture, vegetation, the amount of ice, the rate at which they change, the phenomena of the seasons, all of these things are part of climate. So the framework is the energy balance of the Earth. With that framework, one can begin to make sense and figure out what should be focused on, what should be measured, what should be studied. Then I'm going to talk about what's affecting that energy balance, namely the greenhouse effect. I don't know if we have a pointer here or not. If so, I'll use it. If not, I won't. But then I'll go focus on some of the observations that tell us that things are happening. I'll go through those as quickly as I can. Then, of course, one of the connecting issues with human activities is that of energy usage, namely fossil energy usage, fossil fuels. And finally, I'll close with some comments about what humans can do in the way of mitigating the size of the climate change and adapting to whatever is occurring. So again, the idea of planetary energy balance, the physical energy balance itself dominates the global climate. And I'll illustrate that with a cartoon, which some of you have seen before, which is a depiction of the sun shining down on Earth. Most of the energy from the sun that reaches the planet is in the form of visible and near-infrared energy. And the number 341 indicates about 340 watts per square meter that shines down on the Earth from the sun, averaged over day and night and averaged over all seasons of the year. Now, not all of that is absorbed. Some of it is reflected immediately back to space. In fact, about 102 on an annual average, so that the Earth system ends up absorbing about 239 watts of this solar energy, sunlight, again, averaged over day and night and all seasons of the year and all places on the Earth. So for the Earth to be roughly in balance and not to be heating up just dramatically or freezing over dramatically requires an energy balance. These numbers have been measured by spaceborne remote sensing, as well as some aircraft measurements to fill in gaps. But the outgoing energy is indeed about 239 watts per square meter within less than a watt or so. And that is in the form mostly of outgoing infrared radiation. So those of you who have done any infrared photography will know that you can take a photograph in the infrared of a body if it's warmer than its surroundings, and the Earth is indeed warmer than the immediate parts of space, the vacuum and the cold vacuum that surrounds. So the Earth radiates its infrared energy at about 239 watts per square meter. Now, those numbers are reasonably well measured, as I said. They also fit into another framework, namely, if we know those numbers well enough, and we know how much of the sun's energy is reflected, namely about 30%, we ought to be able to calculate the temperature of the Earth. And indeed, we can do that. This calculation has been done off and on for 40 years as an illustrative exercise. So let me start with Mars in the middle. We can do this calculation for the two planets closest to us as well as Earth, and when we do the calculation for Mars, we get the right number, that the surface temperature of Mars is about minus 28 C, which is with some day and night differences, and it corresponds to what's measured on the surface of Mars. When we do the same calculation for Earth, we get the wrong number. We predict that Earth's temperature is much lower than it is observed to be, that Earth is frozen everywhere all the time. Now, the way we do the calculation is with that simple formula up above, that S, the amount of solar energy reaching us, multiplied by the fraction that's absorbed, or 1 minus the fraction that's reflected, is equal to the black body radiation, or Stefan Boltzmann radiation, sigma, which is a constant, times temperature to the 4th power. Well, if we've measured everything else except T, we can calculate T. We do the calculation, and we get the wrong number for Earth. We calculate that it's too cold. Something's wrong. What's missing is the greenhouse effect, the presence of an atmosphere. With Mars, there is gas around Mars, but it's a very thin atmosphere, low pressure. There's not much carbon dioxide to speak of compared to Earth. With Earth, we have a thicker atmosphere, higher pressure, with some natural greenhouse gases, and that's what gives rise to an Earth which can maintain liquid water, is not frozen, and can therefore maintain life. With Venus, the calculation is dramatically wrong, and some people refer to Venus as having a runaway greenhouse effect, where the atmosphere is so thick, so dominated by CO2 with nearly 100 times the pressure of Earth's atmosphere, that there's a very strong greenhouse effect. So this is kind of one element of proof of the existence of a greenhouse effect. I have other slides which I'm going to skip, but they represent more detailed information of what can be seen from space. So a summary of this energy in the climate system is that if we start with the bottom line there, I've already said that the energy, or the rate at which energy is absorbed from the sun as the input side of the Earth's energy budget is 239 watts per square meter. The top line says, what about human energy usage? We use fantastic amounts of energy: petroleum, coal, natural gas, burning of wood, nuclear power, hydroelectricity, geothermal, you name it, tidal energy. It amounts to a very small number on this scale. It's about 1/10,000th of the sun's energy coming in. So if you were to arbitrarily say, let's take all the human energy usage, just all the human energy usage, including nuclear power, and spread it out over the surface of Earth, how would it come out on this scale? Well, it's 0.025 watts per square meter, or about 1/10,000th of the solar energy coming in. However, it's this middle line, which is, I've called it the extra heat, trapped near the surface of the Earth by this buildup of greenhouse gases, which is due to human activities, dominated by carbon dioxide, that has already, it's adding more than 1% of the solar energy, and this change to the Earth's energy budget has happened roughly in a human generation. So on a geological time scale, the changes that we're observing and that we can account for are very, very rapid, much more rapid than, for example, the rate at which the sun as a variable star might be changing its output. Well, I'll try to get closer to home now with this graph, which many of you have seen. It's a graph of the measurements of carbon dioxide fraction in air on the slopes of Mauna Loa on the Big Island of Hawaii, a series of data that was started in the late 1950s by Dave Keeling at UC San Diego before UC San Diego existed. He was at Scripps Institution of Oceanography, where those of you sitting close enough can see that this graph consists of black dots, which are connected by squiggly lines. Each black dot is the average of a month's worth of measurements taken about every hour. And there are other sources of such data now from all around the world using different measurement techniques, and none of them are as good or as long as this data set. Dave Keeling died in 2004, I think it was, so the series has been continued both by his son, Professor Ralph Keeling, as well as other labs around the world. And what you see is the fraction of carbon dioxide in air has increased over this 55-year time period, 53 years, from about 312 parts per million to this year's value, which for the first time has gone over 390 parts per million. Now, I won't have time today to go into all of the reasons that convince us that this increase is caused by the fossil fuel burning, but there are 6 or 7 lines of evidence that all point in the same direction, including the isotopic content of the carbon dioxide and the way it's changed with time. And I'll show you a couple of other lines, but we're just convinced that this increase, which has been observed now all over the world repeatedly, is due mostly to fossil fuel burning. This is a similar graph, only it stops a year earlier because the red part of the graph shows similar measurements made at the South Pole. And the samples of air that are gathered at the South Pole and sent back to La Jolla for analysis are usually about a year late. So this graph, the red line represents carbon dioxide amounts over Antarctica near the South Pole. You can see that the seasonal changes up and down in fall and winter and spring and summer are not there because there isn't much local photosynthetic activity and decay of vegetation. Thank you very much. Over Antarctica, whereas there is Hawaii, but also the amounts over the South Pole are slightly lower, and that's because the CO2 is being released in the northern hemisphere. It takes about a year and a half to make its way down to the South Pole, so again, everything fits. The next graph shows one of the most stunning kinds of data that again adds to the evidence that this CO2 is unnatural in the sense that it's coming from fossil fuel burning. The time scale on this graph goes back 450,000 years. So 0 on this time scale is current historical epoch, 50,000 years ago, 100,000 years ago, all the way back to 450,000 years ago. And on this graph on top, the red points show carbon dioxide fraction in air extracted from ice cores that have been pulled up, roughly cylindrical ice cores, from as much as 2 miles under Antarctica in dated ice. That is, ice to which you can assign a date. As you go very deep, the time resolution isn't so good. Toward the top of these cores, you can actually tell the difference from one year to another. But what is found when these ice cores are pulled out and crushed in laboratory vacuums and the air interrogated is that in cold times, in glacial times, say 20,000 years ago, the fraction of carbon dioxide was 180 parts per million. In between ice ages, when it's warm, the amount of carbon dioxide is roughly 270, 280 parts per million. The previous ice age, when it was cold, there would be like 175, 180 parts per million. The interglacial warm time would be up to 270, 280, 270, 280, 180, 280, 180, 280. So over the last 4 geological ice age cycles, we've seen this same pattern of carbon dioxide bouncing between the low value of 180 parts per million and the upper value of 280, but never in the range of 390 parts per million. So this is another kind of evidence that what's happening now is different. It's unprecedented over at least the last 500,000 years. These kinds of data now extend back to about 750,000 years, and you see the same pattern. The lower graph simply shows the same graph with methane amounts, which is another strong greenhouse gas. And I won't talk much about methane today, except that when it's been cold, there was about 300 parts per billion of methane in air. When it was warm, about 600, 600, 300, 600, 300, and so forth. And nowadays, methane concentrations are nearly 2 parts per million. So they're roughly 5 or 6 times the cold epoch concentrations and about 3 times the warm epoch concentrations, again, due to human activities, as near as we can tell, at least. The blue graphs here are proxies for the temperatures. That is, how did we know there was an ice age here and the temperatures were low? Again, from isotopic contents of ice in the polar regions. Well, I'll just give you a summary statement that the CO2 increases that have been observed are due to human activities. Roughly 85% of the increased CO2 is due to fossil fuel burning, and 15%, maybe 10% due to deforestation. So that's the burning of wood, the decay of wood products, and the loss of soil organic matter after an area is deforested, usually for agricultural purposes. So I'll just say in passing, too, that the radiative forcing, this change to the Earth's energy balance that I've mentioned, is a little more complicated than I've said. There are some other ingredients like aerosol particles and black carbon soot from fuel burning, but the uncertainties in those quantities are larger, and the greenhouse gases are the part of the energy budget that we can measure and calculate very, very well. For example, another greenhouse gas which is observed to be increasing, again due to human perturbations to the nitrogen cycle, largely through the creation of synthetic nitrogen fertilizer, is laughing gas, nitrous oxide, where the concentrations are a factor of 1,000 lower, 300 parts per billion, but rising globally. And N2O is a very powerful greenhouse gas due to its spectral features as well as its long lifetime in the atmosphere. And the data also extend back to recent ice cores of a couple of centuries ago, showing that the natural background of nitrous oxide was well lower than is now being measured. So the picture's consistent. We can then do calculations, and these calculations can be done, people here at Davis, and this particular set of calculations came from some colleagues at University of Illinois. They're fairly easy to update, and it shows in this jargon I'm using, or terminology, radiative forcing, that the perturbation to the Earth's energy budget, averaged over day and night and a year, is about 2.7 watts per square meter, as I already said. About 1.7 from carbon dioxide, about 0.5 watt per square meter from methane, a couple of 0.1 of a watt from nitrous oxide, and maybe 0.35 watts per square meter from a variety of fluorine-containing gases, including the familiar chlorofluorocarbons, which are not even being used anymore, that were used for refrigerants and aerosol spray propellants until the late 80s for the most part. But even the substitute refrigerants, which are now used in automobile air conditioners and household refrigerators and so forth, like this one, hydrofluorocarbon 134A, the concentration has gone from barely measurable in 1995 up to 50 or 60 parts per trillion. Again, with more in the northern hemisphere, because we're releasing it in the northern hemisphere. It takes about a year to make its way into the southern hemisphere, but the concentrations there are rising too, and the greenhouse effects of these kinds of fluorinated chemicals are also now accumulating, although they're shorter lived, and that's one of the reasons why they were judged to be acceptable replacements to the chlorofluorocarbons. Well, okay, that's kind of a theoretical background and a context. Let me now show you what we're measuring to be happening to climate variables. There are several data centers and scientific groups around the world that are keeping track of temperatures over the planet. This is a depiction from the NASA effort, which is led by Jim Hansen in New York City. And 0 on this graph does not mean 0 degrees. It means a reference level defined as the average over this 30-year period of all the temperatures measured on the surface of the Earth over continents and oceans. If you take all of the data from 1950 through 1979 or 80, this is what they look like, and the average is 0 on this graph. Every period that was colder than that comes out minus degrees centigrade, and then the 30 years or so, starting in the late 70s through now, have been rising pretty consistently almost everywhere in the world, significantly above the noise level of the data. There are several hundred million temperature measurements that go into this record. As I said, there are 2 or 3 other places around the world that work with these temperature data. I'm going to show you some of the results. But here you can see that there was some noisiness in the late 19th century, generally speaking cooler than now, but with fewer data, the uncertainties were larger. A small warming seen in the early part of the 20th century to about 1945, then perhaps a small cooling until about 1975, and then a warming averaged over the whole planet of the last 30 years. Now, there's a lot more detail available, and I'll show you just the next level of detail. If you break up the northern hemisphere north of the equator and show separately the data south of the equator, you see differences already. The red part of the curve are the average temperatures of the half of the planets the north of the equator, and you know that there are more continents than ocean in that land area in the northern hemisphere versus the southern hemisphere in blue, where the planetary surface is mostly oceans. So you see that the northern hemisphere is warming up faster than the southern hemisphere, and these winters of, let's say, 2009 and 2010, which were a little bit cool compared to the previous few years in the northern hemisphere, at the same time the southern hemisphere had an all-time record high. So you begin to see when you go into geographical regions, smaller regions than the whole planet, that there's more variability in the data, and it's worth learning about this. But it's also consistent with the picture that I'm showing you today, that the northern hemisphere is warming up more rapidly because of the forcing that's being imposed on the planet causes land to warm up faster than oceans. There's certainly much more detail. You can go into latitude, longitude plots where for example, the outlines of the continents show here where the equator cuts through the middle. So 2010, which was the hottest of all the 132 years on record, is depicted here, where the first 11 months of the year show that there was a pronounced warming over those in 2010 compared to the reference periods. In the Arctic region, the red and brown false colors show that. It's actually true of all the years recently. 2005, which was the second warmest of the 132 years, again showed a big warming in the Arctic, less warming over the ocean areas, more warming over the central continental regions. This is again consistent with the view that the warming is being caused by this imposed extra greenhouse effect. There's even more data. For example, the month-by-month plot shows that 2011 is going to end up being a little cooler than 2010. There were a couple of months in the middle of this year where the worldwide temperatures were very high, but the early months of the year and the later months of the year are cooler than the previous years. But if you go back to this plot, you'll see that none of the years in the last 20 years have been as low as the reference period in 50 through 80. Even what we thought was a cold winter in 2009 was way above what we used to experience. So it gives you a feeling of where we are. Water temperatures are also observed to be increasing. The data are not as good. Covering the oceans is difficult. We don't have commercial aircraft. For example, we don't have weather stations to speak of over the oceans. So getting oceanic data is more difficult, but such as it is, there are 2 or 3 data sets like this from around the world that show that the heat content of the upper oceans the upper 700 meters or so of the oceans above what's called the thermocline, where the temperature profile changes. These are the ocean waters that are in contact with the air. The air is warming up. The bottom oceans are not in contact with the air on this time scale. So what you'd expect to see is the upper oceans warming up. That is indeed what we see. The amount of energy is at least explainable in terms of the extra greenhouse effect. Sea level rise. Sea level has been observed to be increasing for a long time. People have measured sea level very carefully since about 1880 around the world, but in a very primitive way. It's actually pounding stakes into the shoreline and observing very carefully where the water level strikes the stakes. I'm being a little bit overly simplified here, but that was about it. And what was observed is that, in fact, the average sea level rise is actually different from what would be observed in many places. There are local geological effects going on. There are seasonal effects that have to be sampled over very carefully. But generally speaking, over this 100-year period, from 1880 to about 1990, the amount of sea level rise was about 17 centimeters. So, about this much. So that's about 1.7 millimeters a year, or 17 centimeters in 110 years. Well, the right-hand part of this graph in red shows something a little different. This is the modern era when sea level has been measured by Earth-orbiting satellites using different kinds of radar techniques that measure the height of the sea level very accurately. And what those data are showing, if you look at them in more detail from 1991 or so, is a much better, stronger record scientifically, where we have many more data, where we can obtain a proper global average, and where the rate of rise of sea level is twice what we had deduced, nearly twice as big, 3.2 millimeters a year instead of 1.7 over this 20-year period. So we know that sea level's rising, and when these data first became available a few years ago, it wasn't clear where this was coming from. It is clear that some of it is coming from the expansion of seawater due to the warming of seawater. Even though water doesn't expand much, when it is heated, it expands a little bit, and that accounts for a fraction of this rise, a third or a half of it. But the additional part of the explanation for why sea level is rising now has also become clear in the last few years. It's due to the loss of ice on Greenland and Antarctic continents. And these measurements have been done in a way that some of you know about. It's from a gravity sensing satellite. In fact, it's a fleet of satellites that trail each other and measure minor perturbations to the Earth's gravitational field. Not only can the satellites detect that the Earth's gravitational field is not like a perfect sphere, but if something changes beneath, the time change in the gravitational pull on the satellites can be observed. Like, for example, the amount of water in aquifers beneath parts of India can now be detected with these satellites, and they've applied the method now to measuring the amount of ice over Greenland, and the best fit to the data now is a small acceleration. That is, not only is the amount of ice on the Greenland continent decreasing, but it's decreasing in an accelerated way, and these show the numbers, so that if you averaged over this 9-year period, you'd obtain about a 0.7 millimeter per year sea level rise. If you take the most recent part of the graph, it's more like 0.9, and the same thing is available from Antarctica. This is most impressive science, in my opinion. Very high-tech science, but very accurate, I think, showing seasonal changes in the mass of ice over Antarctica, but again, an accelerated loss, and again, with quantitative measurements of how much of this continental ice is now floating in or melting in the oceans, giving rise to sea level, a sea level rise. I'm going to skip a couple of things about Arctic sea ice. So we have then records that the air temperatures are increasing, especially over the last 30 years. We have evidence of the upper parts of the ocean heating up, of sea level rising, and of ice being lost at both poles. I implied that there's something distinctive about this last 30 years. It's not just that the temperatures have been going up out of the range, out of the statistical range at all of our 30-year reference period, but also it's distinctive because during this 30-year period, scientists have actually measured the output of the sun, that is the energy coming to us from the sun, in a reliable enough way to be able to say, well, is the sun causing this warming? Is the sun causing these climate changes or not? And the answer is no. This is a composite set of data showing the energy output of the sun at Earth orbit, and it shows a cyclic behavior, an 11-year cycle just like the sunspots, which is periodic. That is, the amount of energy reaching the Earth from the sun is not increasing. So those of us who wanted to be able to say that the sun was somehow becoming brighter, causing the planet to warm up, we can no longer say that due to data like this. These data are from Judith Lean, a physicist at the United States Navy Research Lab, and her colleague Klaus Freilich in Switzerland. And Freilich has extended the data by patching together other satellite instruments showing that even into this current solar cycle, which has been a weird one where there was a pronounced minimum for several years, the results, again, the sun's energy reaching the Earth has not increased. So that you end up concluding that the energy balance and calculations from it do explain the warming. I'm just showing a spaghetti chart here of calculations showing that when people use the best available energy balance and climate model calculations, they can reproduce the observed temperature with this range of model calculations, whereas if they try that same calculation to reproduce this observed temperature, they cannot reproduce the temperature that's been measured unless they include the increase in greenhouse gases. So there's evidence in both kinds of logical sense here that the warming, at least, that's been observed has been proven to be due to the extra greenhouse effect within all reason, I think. Well, how do we connect this then with what humans are doing a little bit more strongly and where we go in the future? There are groups around the world who keep track of fossil fuel burning, and I'm showing here a graph from one of the better efforts at Oak Ridge National Laboratory, and I just got this update from them last week. But it shows the historical use of fossil fuels worldwide, in this case since 1850, broken down into solid, which of course is coal and wood, liquid, which is petroleum, natural gas, the release of carbon dioxide due to cement manufacture, and then the flaring of natural gas. And it shows a very strong increase so that by the year 2010, human use of these carbon-containing fuels amounts to over 9 billion tons of carbon in the form of carbon dioxide annually, whereas as recently as 1930, that number was less than 1. So the growth has been really pronounced, and the growth from 2009 to 2010 was really quite strong. There was a little bit of a fall off in 2009, but a large jump again in 2010. Well, the demand for energy, of course, can be seen in world marketed energy consumption, where these are data from this semi-independent agency inside the Department of Energy using the weird units that they use, quadrillion BTUs. But to the left of the blue line is obviously historical data. To the right is projections into the future. As recently as early 70s, world energy usage was about 200 of these units. It had doubled by about 2,000. It's projected to increase about 75% in the next 25 years, largely due to the growth in developing countries and world population growth. Just to give you one tangible example, a measure of coal consumption worldwide shows historically that, let's see, I guess I don't have the US on this curve, but largely the historical data, the U.S. was the biggest user of coal, but by the year 2008, China's use of coal surpasses that of the rest of the world because China has been on a rapid economic development curve, as well as doing a lot of the heavy manufacturing for the rest of the world. So this is just a tangible example. Well, where does this all leave us and lead us in terms of climate change? This gets into a whole new enterprise of large-scale mathematical modeling of climate. I just have the cover of one of our reports from last year, a committee that was chaired by Susan Solomon that was focused on what would be the targets for stabilizing Earth's climate in terms of greenhouse gas emissions. And in the process, they did a critical review of future climate changes, which are projected by the mathematical models of today, which are basically the governing equations for the planetary system of air and water and soils, and the conservation of energy and mass and the flows and angular momentum, and try to solve the equations from first principles. And they reviewed then what are the future projections of temperatures, averages, and summertime highs, precipitation amounts for various regions and seasons of the world, frequencies of heavy rainfalls, Arctic sea ice cover, wildfire frequencies, and many other impacts. And suffice it to say, these projections are, I think, reliable enough to give us ranges that the perturbations that will be seen in a future use of fossil fuel energy like this are significant. Now, I didn't say that this world marketed energy consumption, about 85% of it is due to fossil fuel burning. There is some non-marketed energy, like the use of animal dung and wood that's gathered up on a daily basis, which are a few percent. But for the industrialized world, certainly 85% of the energy is from fossil fuel, and until and unless that changes, the CO2 emissions will lead to the kinds of, as far as we can tell, to the kinds of predicted model results which Solomon and her crew summarized. Okay, well, how are humans going to respond, and why is this an issue of today and for the future? Well, there are two kinds of responses, and I'm sure you've heard this terminology, but mitigation we define as actions which are taken to reduce the pace and the amount of climate change which is caused by humans. Now, at the same time, there can and will be climate change caused by nature, we presume, but these are the factors that we know about over which humans have control. So mitigation would be any effort that is taken to reduce the amount of that climate change, whereas adaptation would categorize those human activities which are being taken to reduce the adverse impacts of climate change from the climate changes that do occur. I'll show you one example, which is a paper depicting the huge heat wave that they had in West Central Europe in 2003. Some of you remember that Paris was especially hard hit July and August of 2003. These data represent averages of the difference from the normal July and August in Paris over a period of time, showing the actual data of what happened to the July average temperature. And then 2003 on this scale was a couple degrees centigrade on average higher for a whole month, but it was a severe heat wave, and I think there was something like 12,000 additional deaths reported in Paris which were attributed to this heat wave. The model calculations that go into the future show that that kind of a heat wave, while it was a 1 in 300 year event historically, will become a 1 out of 2 year event by about the year 2040 or 2045. So it's an example of the need both to do mitigation to try to slow down this climate change, but at the same time take those adaptation steps towards, for example, air conditioning, better air circulation, better hydration of especially old people who are especially susceptible to heat waves. Mitigation actions, of course, are things like reducing the CO2 emissions from fossil fuel usage. And those actions could be anything from energy efficiency, to simply use less fuel to get the amount of energy that we really need, the use of renewable energy, nuclear power, maybe carbon capture and sequestration, also to minimize the emissions of carbon dioxide from forests and soils by stabilizing and regrowing forests, and all the way down the line with different greenhouse gases and black carbon. A way to depict this challenge, it's actually global carbon cycle management, where this is a cartoon that was given to me by a Japanese colleague several years ago, and I really should update it because it's meant to depict water rising in a bathtub, where eventually the water rises to a point that the bathtub can't hold it anymore, and that would be an analog or a metaphor for a dangerous amount of CO2 accumulation. And the way that the level in the bathtub is determined, of course, is by the input, which is the human-caused emission of extra carbon dioxide. And in this depiction, it was only 7 billion tons of carbon per year. We now know it's over 9, whereas the natural absorption uptake, or the outflow of the bathtub, is about 3 billion tons of carbon dioxide. So when you've heard people say that we're going to have to reduce the input of our emissions of greenhouse gases by 2/3 or so, that's not inventing a number. It's based on what we've been able to measure of the planet's natural ability to take up carbon dioxide, either by oceans or lands. And there are several independent methods by which these numbers have been arranged. We can talk about it later if you wish. So the management challenge is to stabilize the water level in the bathtub at some level. We're going to have to decrease the input, because it's not clear that we can ever increase the natural absorption capability. But now we have a challenge of scale, which shows the amount of human intervention that's going to be needed. To stabilize the atmosphere, for example, at 500 parts per million carbon dioxide in the middle of this century, will require reducing the CO2 emissions by about 7 billion tons of carbon per year. And each billion tons of carbon would require, for example, that the energy use in every building on the surface of the Earth would have to be cut by 20 or 25%. So some of you are familiar with the energy efficiency that's been built into some of the new campus buildings here. We would have to decrease the energy use in every building on the planet by 20 or 25% to be able to avoid 1 billion tons of carbon as carbon dioxide emission per year. Or we would have to increase the fuel economy of 2 billion cars on Earth to 60 miles an hour from 30 miles an hour. That would save you 1 billion tons of carbon emitted per year. Or if we could ever find a way to capture the CO2 emission from a coal-burning power plant, if we could do that from 800 1-gigawatt plants worldwide, we could save 1 billion tons of carbon per year. These examples are just meant to show you, and they're from our colleagues Steve Pacala and Rob Sokolow in a great paper they wrote in 2004, just to give you an idea of the challenge of scale. Now, the low-hanging fruit, which some of you have mentioned today, is energy efficiency, because here's a way to save money and mitigate climate change at the same time. Energy efficiency would do all of these things. It would decrease our dependency on foreign oil. It would improve national security for obvious reasons. It would decrease our trade deficit, which at $100 per barrel of oil is roughly $400 billion a year of expenses. It would decrease local air pollution. It would increase national competitiveness on manufactured products. It would encourage the development of new products for global markets. And it would decrease household energy costs, which we all understand, while it would also slow down the increases of carbon dioxide and methane. So energy efficiency looks like a winner, and you really wonder why we haven't been able to make a stronger national commitment to doing it, like we did after the oil embargoes by OPEC in the late 70s. We made great increases in energy efficiency in those years, and then we stopped. If you want to put it in more practical terms, maybe, we have two strategic challenges. One is to reduce the amount of oil we use for transportation. That could either be through energy efficiency or going to a fleet of electrically powered vehicles, which requires new technologies of all kinds, which many of you, we don't have to go recite them here, but at the same time, we have to reduce the carbon dioxide emissions from coal-fired power plants, either by keeping the same plants and sequestering the carbon dioxide, or increasing their efficiencies, or replacing them, or whatever. Adaptation possibilities, and I'm going to conclude now, certainly include changing agricultural cropping patterns with some very important details, to develop heat, drought, and salt-resistant crop varieties, to deal with, obviously, decreased water availability in some places and increased evapotranspiration rates. We have to strengthen public health and environmental engineering defenses against a possible incursion from tropical diseases. By the way, this list is from John Holdren from a talk he gave in 2008 before he became science advisor, although I think you would arrive at the same list of adaptation possibilities and desires. To build new water projects, both for flood control and drought management, a healthier system of water reservoirs. And then, of course, sea level rise. In certain parts of the world, you can justify building better dikes and storm surge barriers. And then, of course, from a financial and capital efficiency point of view, to try to avoid further development on areas which are really prone to frequent flooding or sea level rise. I think I'll stop here. I've taken a little bit too much time, but I wanted to introduce as many aspects of the climate change situation as I can, both the scientific basis, some of the evidence that we have real changes underway, which are very likely due to human activities, the special role of fossil fuel usage, and then the enormous range of challenges that we have to us right now. But as I said before, some of those challenges do represent opportunities for new businesses as well. So let me stop here, and thank you again for the invitation.
We thank you, Ralph, for this compelling and inspiring but sobering talk. And now we open the floor to questions. We have 2 microphones in the back. And if you have questions, would you line up the microphone? And we'll have some time for questions. Yes?
I was wondering what your opinion on geoengineering is. What are some of the benefits and the consequences?
Can you just repeat a little bit more slowly? I think I understood, but can you repeat it?
What is your opinion on geoengineering? What are some of the benefits and the consequences?
Well, there have been some suggestions on how humans might be able to intentionally intervene on a large scale to slow down or prevent climate change in this case. I have a depiction of one of the schemes here, which would be to somehow reflect some of the incoming sunlight back out to space by either putting material in orbit around the Earth, such as the gravitational neutral point at L = 1, light material which could reflect a fraction of the sunlight back out to space, or maybe spraying sulfur-containing material in the stratosphere where they could possibly be engineered to be very fine particles that would be light-reflecting and which would survive long enough that the replacement cost of the sulfur wouldn't be too great. And in principle, there are some ways that could reflect enough of the sunlight back to space to perhaps affect the planet's energy budget and to mitigate climate change. I think this topic should be researched. I think it should be done on paper, not real experiments. Until recently, most people have said we don't want to touch it, we don't want to do research, we think it's too dangerous, we think it's more likely to lead to bad side effects. But I think we need some research understanding of what might happen, and I think paper-type research, theoretical research, is a good investment. There is another interesting idea that I think was more benign, and that was to try to fertilize the world's oceans in a limited way in those regions of the world's oceans where you can tell that the limiting nutrient is iron rather than nitrogen or phosphorus. With a relatively small amount of iron, it might be possible to trigger a burst in photosynthetic activity to draw CO2 out of the air. In fact, it's been shown that it works in like 5-kilometer patches of ocean. But to make the solution one that would actually stabilize climate, you have to take the newly formed organic material that you could seed by this extra photosynthesis and get it to sink. So originally this idea was called the geritol solution, give it a little iron. But I think what would really be needed is like a Chicago solution, where you have to bury the gangsters in concrete all the way to the bottom of the ocean. And the experiments that have been done have been very good science by biological oceanographers and chemical and physical oceanographers, but they don't look very hopeful. It doesn't look possible to remove enough carbon dioxide from the air to overcome the fossil fuel. In the meantime, the oceans are also acidifying due to the extra carbon dioxide amounts, so even if people could come up with a way to engineer reflecting material that could possibly stabilize the climate change, at the same time, the fossil fuel CO2 is causing the oceans to become more acidic, and we wouldn't be solving that problem. So I do favor research. I don't think we should bet on these techniques, but I think we need them partly to discourage people from making really dumb ideas and doing things that would be dangerous. I think we need a research base, possibly as an offensive 30 or 40 years from now, but more likely as a defensive strategy against really dumb ideas being implemented.
Now we come to this side.
Would you please explain the issue of climate sensitivity and where the models on that now stand?
Yeah, it's a term of art meant to describe if you do a calculation where you're trying, for example, to calculate a temperature rise due to a certain input, like a certain input of carbon dioxide. Climate sensitivity is meant to be a measure of how sensitive your model is to the input. That is, what bang do you get for the buck? How much temperature rise do you get out of so much CO2? And the sensitivity is due to two main factors. One is the direct radiative effect, which is really easy to calculate, of the, let's say, CO2 or other greenhouse gas trapping energy. And the second part of it is due to feedbacks. For example, water. So as you warm a body of water, evaporation increases, as you know, in a disproportionate way with temperature. So a simplistic and likely correct answer is that as water warms up, there will be more evaporation, there will be more water in the air, and that water has an additional greenhouse effect, which then adds to your calculated sensitivity. So some of the uncertainty in climate models today and some of the disagreement is how much extra heat trapping do you get due to that particular feedback. But there are several other feedbacks built into the system that we know are working. We just don't know which one is the most important and how it will be manifest. So this climate sensitivity is a term of art describing some of the give and take of these variables in the calculations. If I understood your question, that's my answer.
Well, what I was getting at was where is the research? Hansen, I think, originally proposed that doubling CO2 would raise 12 degrees. And I'm just curious what the consensus is now.
Okay. Well, a doubling of CO2 gives about 4.5 watts per square meter of forcing. It's then a question of what the models do with that extra heat trapping. The original calculations by Arrhenius in the late 19th century calculated about, I don't know, 3 or 4 degrees centigrade rise. The current models calculate about 3 or 4 degrees centigrade rise, but anything between 1.5 and 5 is still calculated by today's models. I don't think Hansen ever calculated 12 for a doubling.
Okay. Yes, please.
Thank you very much. I think part of my question has been addressed, but my concern was on the part of the mitigation that you mentioned is the CCS, which is the carbon capture sequestration. I was involved in a design project to capture the carbon from a Dragg's coal-fired plant in the UK. So our proposal was to capture, then liquefy it and store it in a tank, ready to take it somewhere else. But we had a challenge with the storage. So if you capture this carbon dioxide, so how do you store it? What volume can you store, and where do you store the carbon dioxide? So that was the main challenge, and this is the question which I have, which I think maybe you can address. Thank you.
Are you a technical expert on the subject?
Not really. I was part of the students at University of Leeds who were assigned, this project to design the carbon capture plant for the Dragg's coal-fired plant.
Yeah. Well, perhaps there are some experts here today who have thought seriously about capturing carbon dioxide, let's say from a exhaust plume, or decarbonizing fuel before it's burnt to use the carbon elsewhere. This is a huge challenge. I think it absolutely needs focus, although I don't hold much hope myself that it will end up being a bulk solution for several reasons. First of all, a lot of our fuel burning takes place in dispersed places, for example, like automobiles and individual homes. The easy target would be high concentration CO2 plumes from power plants. But even then, the bulk amounts are so large, the efficiency of capture, the energy used in capturing, and then the energy used in transporting the stuff, let alone liquefying it and pumping it underground and assuring that it can stay for a long time. These are all challenges, but the reason I think we have to face it is that it's unlikely that we're going to come up with one simple solution that handles the whole fossil fuel dilemma. We're going to have 5% here, 10% there, maybe 20% from energy efficiency and so forth. So I think carbon capture and sequestration needs more work. It's going to be a small application when it does work. I don't see any way that it's going to solve the whole problem by itself, but we are required to at least try it, I think.
Okay.
Thank you.
I thank you very much for calling out energy efficiency as part of the solution. I'm the director of the Energy Efficiency Center here at UC Davis. I work primarily with engineers, but I'm a sociologist, and one of the things that very much concerns me is the focus both in funding and reports on the natural sciences and engineering, on devices, and very little on the social science part of it. As your talk says, this has got human causes. And unless we change the way we govern, organize, consume, we are not going to solve this problem. Those are cultural and institutional and governance problems, and we are not, as a scientific community, addressing those in a very substantial way. And I'm very, very concerned about it. I'd love to hear what you have to say. Thank you.
How could I disagree with that? There is a set of data that I have here that some of you know very well. It's a success story from California where some of the above that you mentioned was actually applied, and that is refrigeration efficiencies in California. First of all, I don't know how many of you know that Californians use about 50 to 60% as much electricity as the rest of the United States on average per person. So California is electricity efficient. Now, how did that happen? Well, back in the 50s and 60s, the biggest single consumer of electricity in a typical house was the refrigerator. And people kept wanting bigger refrigerators, and the annual cost of electricity, the cost of the refrigerator, and the electricity usage was rising. But in the late 70s, a bunch of things started to happen. Electricity prices got big enough that public policy started proposing that there be standards for energy efficiency of refrigerators, compressors, the motors, the insulation, and some people objected. This is government intrusion. It's going to cost so much that nobody will be able to afford a big refrigerator. It's going to bankrupt us. But nonetheless, California went ahead with standards on electricity. Another thing, and now if you see the data through 2010, the size of the refrigerator, this is the average volume of a refrigerator, it's now about 23 cubic feet. And what limits the size of a refrigerator today is not the cost, it's the width of the kitchen door. Refrigerator prices have gone down from nearly $1,300 on average to, say, $500 or $400. The efficiency has gone way up to the point that the refrigerator is no longer the biggest consumer of electricity in California. This efficiency story has led California to be more electricity efficient than the rest of the country. But another kind of intervention was needed, and that was decoupling revenues to utilities from their volume. So utilities are allowed to charge higher prices for electricity in California during hours of peak demand, and that has forced all of us as Californians to use electricity more efficiently. So it's been a combination of technology, public policy, and even regulation that has led to this kind of success story in California. So you're absolutely right, and we should be making more people aware that things can be done.
Yes.
Thank you. You concentrated on the contributions to greenhouse gases from man-made sources, but to what extent are we at the peril of natural catastrophes, for instance, volcanoes and, God forbid, the occasional giant meteor? Do not volcanoes contribute a considerable portion? Do you know what the fractions are compared to the man-made contributions?
The volcanic input is hard to measure. There are measurements out there, and it's a reasonably big number, but you can see that the increase, the change in CO2 concentrations that's been observed is due to fossil fuel usage by what's called the Seuss effect, the ratio of carbon-12 to carbon-13 and carbon-12 to carbon-14 in the atmospheric CO2, which shows that it's fossil fuel derived. So, of course, there's CO2 emitted by volcanoes. But it's not the dominant in the carbon cycle in the first place, and the isotopic ratios don't match what's observed in the atmospheric change, whereas the fossil fuel figures do match. There are other natural sources of greenhouse gases, of course, including water vapor.
Thank you.
This may be a politically incorrect question, but do you know of any other intervention that would be cheaper and more efficient than birth control pills to control the CO2?
Yes, the answer.
Okay. All of us have our favorite thing to blame here, but let's just talk about CO2 emissions. You can talk about all kinds of other impacts and effluents, but you can break down this into a truism that the CO2 emissions per unit time can be broken down into three factors. The emissions due to a unit produced, like producing a pair of shoes or manufacturing an automobile, whatever, multiplied by the number of units, number of pairs of shoes or automobiles per person, multiplied by population. So you can see from this kind of a factorization or a disaggregation, that all of these factors are involved. So population definitely has a proportional effect, but so does the measure of material consumption, so does the technology or the inverse of good technology, namely the amount of waste or the amount of emissions. So that you ask if I know of a cheaper way. I think I do. I would probably focus on energy efficiency to start with, but certainly to some extent, population is a proportionality factor. I think that's just true.
Thank you very much.
Hello, Dr. Cicerone. I hope you'd share a few of your thoughts about two topics. One is abrupt climate change, and the other is what's often been called the methane time bomb from methane clathrates or melting permafrost, and the potential for those types of feedback loops and abrupt change like thermohaline circulation.
So was it potential for abrupt climate change? Possibly due to clathrate breakdown?
Yeah, if,
Was there another factor that you mentioned?
Rapid release of methane would be one, and then changing of the ocean circulation, thermohaline circulation.
Yeah. Well, there's a lot that we don't understand about the climate system and its dynamics, so there are a lot of possibilities. The methane one I know more about, and that is that there are colossal amounts of organic matter that have been produced over Earth's history, some of which have, as you know, been converted into coal or petroleum or gas. And in the case of gas, there are these structures called methane clathrates, which are individual methane gas molecules trapped in a structure of basically a kind of semi-crystal of water around it. And this structure can be made stable under enough pressure, low enough temperatures. And we know these things exist. Probably the best data are in the hands of oil companies and gas companies. They exist around the margins of different continents and in some ocean bottoms. And some of those areas are vulnerable to pressure changes above or to warming of the water and having enough heat go down into the semi-frozen regions. And now if that were to happen, a great deal of methane could be released, and also methane in permafrost regions, because so much organic matter has been accumulated there, there's a lot of methane. So there are a lot of geochemists and geologists who've been thinking about prior changes in climate over geological history and whether any of them rapidly observed, that is, changes that happen rapidly, whether they happen due to a rapid release of this trapped methane in geological past, and of course whether it can happen today. And the answer is yes. But it's hard to be quantitative. We don't know all the quantities involved, although we have pretty good estimates of how much methane is trapped in these formations, where the unstable ones are, and how much heat it would take to destabilize them. I would say methane in permafrost is another area of vulnerability. I will say one thing. In the last 20 years, what's been known about past climate changes on the Earth has changed our view. If you go back to old encyclopedias, you'll find that people said climate changed slowly over thousands and millions of years. But people began to discover exceptions in the record of fossils and isotopes and sediments that showed that some previous climate changes have happened rapidly. In fact, more rapidly than the time resolution of the data that were being used. So now it's become, with enough of these exceptions being shown, it's more like the norm of what we think past climate change have happened rapidly and more abruptly than the slow changes. So I'm waving my arms because I think that's where we are, but there's some really good ideas out there, and they are amenable to scientific investigation.
So before we take the last two questions, I want to invite everyone to the reception afterwards, and you can ask Ralph questions informally then. Okay, please.
I'd like to ask, because I think you've made a very good point of talking about research and talking about the need to study things. I'd like to ask what your opinion, the role of organizations like the National Research Council or the National Academy of Science, and what responsibilities of individual sciences are to address these issues with more than just saying we need to do more research?
Well, I think to be true to the scientific process, I think we always have to say that this is what we understand now, and that it's subject to criticism, it's subject to refinement. So, for example, there are societies of scientists and engineers who have made public statements, and these statements have been vetted, they've been researched, they've been voted on, and they're posted publicly in various places saying a short version of what I said, that climate is changing, that the best evidence we have today indicates that most of this change over the last 30 or 40 years is due to human activities. Here's what the activities are, and that obviously detailed predictions at the level we want are not available yet. Now, that's an important role for individual scientists and scientific societies like the American Chemical Society, the American Physical Society, the American Geophysical Union, academies of other countries, our own, the Ecological Society of America, the American Meteorological Society, the Geological Society. When these scientists say that this is the best of our ability right now, this is what the evidence is saying, that's a pretty powerful statement, and I think it's a responsible one without going overboard and saying we know exactly what to do. So that's one measure, I think, making public statements which are responsible. To be more politically active, I think, gets down to individual choices. And every time any one of us stands up in the political arena and makes statements which are value judgments or our own opinions, I think we have to take pains to label them as such and to show where we're departing from what is purely objective and scientific and what gets into the realm of personal opinion and value judgments. And I think each one of us has the option to make those statements. But I think it's incumbent on us to separate them from what can be demonstrated objectively.
Thank you.
Okay.
That's a conservative, cautious point of view, but that's where I am.
Okay, last question.
Okay. I wanted to ask you, how aware are other countries about this problem? Because those are some very alarming charts you showed us, and I fear whatever margin of safety we're able to create for ourselves is just going to get eaten for breakfast by developing countries. You know, for example, India, the Middle East, Russia, and China especially. If it turns out they're actually, for all the people that live over there, they're consuming much less than individual Americans are. And once they're given time to finally catch up to our standard of living, it's going to be like there's not like 8 billion people living, but in today's terms, it's going to be like 72 billion people living on the earth if everybody catches up to the same standard of living. So I feel like we're at this hypocritical stage of, you know, we were allowed to develop using fossil fuels, pretending that was an inexhaustible source, and other countries are beginning to do the same. They're building their own Americas at a grander scale, and I believe politics should be an integral part of this.
Well, of course, you're absolutely right. And one of the reasons that international agreements that would have a real impact on limiting climate change have not been successful yet is that disagreement that you just outlined. Namely, if you look at, for example, at energy use patterns, I don't have the graph I wanted with me, but in the past, the bulk of the energy usage worldwide, which I said is about 85% fossil fuel usage, was due to developed countries. And I mean, as recently as 1990, the big fraction of the energy usage was by the United States, Canada, Western Europe, Japan, Australia. But as you move into the present and the near-term future, almost all of the growth is now by the developing and emerging market countries. So when the government-to-government or even people-to-people discussions occur, there are these two different points of view. That, first of all, carbon dioxide as a representative greenhouse gas survives in the atmosphere for hundreds of years, so that what was put in the atmosphere in the year 1950 is still there, so that one could say from the point of view of a developing country, well, look, what's in the atmosphere now was due to you rich people, but the rich countries can turn around and say, but what's going to be in the atmosphere in the next human generation is largely due to your development. So coming up with an equitable share of the responsibility so far has not reached agreement. And the per capita emissions, as you say, are another difference that has to be taken into account. And so far people haven't been able to agree. I mean, I have my own opinions, but that's essentially the problem as you outlined it. So I don't know how to break that deadlock.
Okay, so let's thank Ralph again for this discussion.